to help us understand the connection between polls and the probability theory that we have learned, let's construct a scenario that we can work through together and that it's similar to the one that pollsters face. We will use an urn instead of voters. And because pollsters are competing with other pollsters for media attention, we will imitate that by having our competition with a $25 prize. The challenge is to guess the spread between the proportion of blue and red balls in this urn. Before making a prediction, you can take a sample with replacement from the urn. To mimic the fact that running polls is expensive, it will cost you 10 cents per bead you sample. So if your sample size is 250 and you win, you'll break even, as you'll have to pay me $25 to collect your $25. Your entry into the competition can be an interval. If the interval you submit contains the true proportion, you get half what you paid and pass to the second phase of the competition. In the second phase of the competition, the entry with the smallest interval is selected as the winner. The DS Labs package includes a function that shows a random draw from the urn that we just saw. Here's the code that you can write to see a sample. And here is a sample with 25 beads. Okay, now that you know the rules, think about how you would construct your interval. How many beads would you sample, etc. Notice that we have just described a simple sampling model for opinion polls. The beads inside the urn represent the individuals that will vote on Election Day. Those that will vote Republican are represented with red beads and the Democrats with blue beads. For simplicity, assume there are no other colors, that there are just two parties. We want to predict the proportion of blue beads in the urn. Let's call this quantity P, which in turn tells us the proportion of red beads, 1 minus P, and the spread, P minus 1 minus P, which simplifies to 2P minus 1. In statistical textbooks, the beads in the urn are called the population. The proportion of blue beads in the population, P, is called a parameter. The 25 beads that we saw in an earlier plot after we sampled, that's called a sample. The task of statistical inference is to predict the parameter P using the observed data in the sample. Now, can we do this with just the 25 observations we showed you? Well, they are certainly informative. For example, given that we see 13 red and 12 blue, it is unlikely that P is bigger than 0.9 or smaller than 0.1, because if they were, it would be improbable to see 13 red and 12 blue. But are we ready to predict with certainty that there are more red beads than blue? Okay, what we want to do is construct an estimate of P using only the information we observe. An estimate can be thought of as a summary of the observed data that we think is informative about the parameter of interest. It seems intuitive to think that the proportion of blue beads in the sample, which in this case is 0.48, must be at least related to the actual proportion P. But do we simply predict P to be 0.48? First, note that the sample proportion is a random variable. If we run the command take_poll25, say 4 times, we get 4 different answers. Each time, the sample is different and the sample proportion is different. The sample proportion is a random variable. Note that in the 4 random samples we show, the sample proportion ranges from 0.44 to 0.6. By describing the distribution of this random variable, we will be able to gain insights into how good this estimate is and how we can make it better.